Okay, we're going to be talking about electric circuits, and the goal here is to get you to know enough about circuits so you can do work with the Arduino computer programmable computer boards. We're going to be doing two labs based on those, but you have to have some basic understanding of what electricity is. So I want to make sure everybody's up to the same level. We're dealing with direct current, right? Not alternating current like you get when you plug your into the wall in your home. This is direct current is in one direction, in other words. All right. Well, so the electricity is just basically the flow of electrons, or more accurately, probably would be to say it's a flow of the charge associated with electrons. The battery, in other words, the battery. In this case, we have a circuit here. The black is essentially the wire, and this is a schematic symbol used to describe a battery. Battery carries a voltage, which is essentially a potential energy between one pole and the other. So if you have what happens when the electron runs from the negative pole of your battery through the wire back to the positive, it's lost that potential energy. It's gone from the higher to the lower potential energy in your battery. In that way, a battery is much like a pump. If you think of this as instead of electric current wires, think of this as a pipe carrying a flow of water. A battery is much like a pump. It's basically increasing the energy content of the water, enabling it to flow through this like circuit or closed loop of water. There is one thing you need to be aware of when you're talking about electric flow and how it's the notation, sort of the convention for how it's noted, is that the flow of electricity is counter to the flow of electrons. So while we like to think of our little electrons zipping around through here, in this case clockwise, the flow of electricity when we're speaking to each other or to physicists or electrical engineers would be counterclockwise from the positive pole back to the negative pole of our battery. All right, you need a closed circuit. In this case, the simplest thing you can do is to break the circuit with a switch. In this case, it might be like a knife switch, which essentially opens up, does not allow for a flow of electricity. So in this case, on the left, we have no flow. On the right, we have the same circuit we were dealing with previously. So a closed circuit, that's a good thing. Open circuit means basically someone's opened up the circuit, like you broke the circuit so that you have no flow occurring. So we introduced the concept of a battery. Now I'm going to introduce one more concept, that is of a resistor. A resistor does exactly what it sounds like. It resists the flow of electricity. So if we were to insert a resistor into our circuit like we have here, we're going to have less current flowing through it. The voltage is still the same. The voltage is determined purely by the battery. But in this case, we're going to have less flow of electrons. So we're going to have less current. Oh, and I didn't really introduce the term current, which I'm going to do in the next slide. So we're going to actually introduce three terms: voltage, current, and resistance. And these are the symbols V, I, and R that are used to represent those three properties. Voltage is the difference in potential energy per charge between 2 points, like between the 2 points in our battery. The units are volts, and it's used with the symbol V to represent volts. The current is the flow of charge, and it's actually flow of charge per unit time, and it's going to be known in units of amps, and the letter we use to symbolize that is A. And lastly, a resistance, R, is resistance to our current flow. Again, it's like a impedance to the flow of electrons. Might be like if we think of our water analogy, like a restriction where maybe the flow is a smaller diameter pipe. And the units are ohms, and it's represented by an omega, letter omega, capital Omega. All right, so we have this thing called Ohm's law. Basically, a very simple relationship between V voltage, I current, R resistance, where the current times the resistance simply equals the voltage. So if you know two of them, you can obviously calculate the third. So in many cases, we might know the voltage and resistance. Those are basically from the components that we're dealing with. So we have the V of some particular battery. We buy a resistor with particular ohms, number of ohms, and we can calculate the current that we'd expect to see in a circuit like this by simply dividing V divided by R, and we'll end up with I, the current. So let's imagine that we wanted to add an LED. An LED is just simply like a small light. These LEDs are rated for the amperage that they can handle. So you might imagine we're adding one that can handle only 20 milliamps. So if we're in this circuit here where we have no resistance or no resistor, we have only the resistance of the wires, and I've represented that by 0.01 ohms. And so if we calculate, so we're going to substitute into Ohm's law. We have 9-volt battery, resistance of 0.01 ohms. Here we have, so it's 9 volts equals I times that quantity. Calculate for I. We find that the current is 900 amps, which is about like several thousand or 10, 20,000 times greater than what the LED is rated for. Not a good idea. You're going to blow out that LED. So what we do is we're going to put a resistor into our circuit, and we can actually calculate the size of the resistor that we might end up needing using Ohm's law, and we get one that might be rated at, say, 500 ohms. That would essentially reduce the current to a level that we could insert this LED without blowing it out.